Everybody have a copy of the notes for today? Well, we've got a final exam in less than a week, so I hope that the brief quiz that we just did will give you some ideas on what to study. Like I was mentioning earlier, you should be prepared for any of the software packages that we've covered this semester. It's a comprehensive exam, meaning that the whole course will be represented on the final, but there's added emphasis on the material we've covered since the second midterm. So that means more of the points will be coming from, on like sort of a per week basis, more of the points will come from the recent material, and the more difficult questions will be on the recent material rather than writing a really hard question with lots of points for the first weeks of the semester. It'll be focused more on the recent things that we've done. So you're allowed to prepare a one-page equation sheet and bring that on the day of the final. You can use it on the second part of the exam. Like the first two midterms we've had, there's going to be a conceptual part of the exam that's covering the short answer type stuff, and then there's going to be problem solving / computer problems for the second half. We'll have 2 hours, so there may be like one extra question compared to the length of the midterm exams where we only had 75 minutes available. Any questions about the announcements? All right. This is where we left off, is talking about underground aquifers. And the example that we solved in class on Tuesday was for a confined aquifer, meaning that there is a layer of clay or rock or some other confining material both above and below the saturated zone in the aquifer. In this case, an unconfined aquifer doesn't have that upper confining layer. It does have a confining layer underneath, which is why the water is pooling here. We have a free surface of water underneath the ground, but it's perched on top of a confining layer. You can see that in this case, the drawdown is of the physical surface of the water, whereas back if we switch to the confined aquifer, the water surface isn't changing. What's changing is what's called the phreatic surface or the piezometric surface. This line is a graph of the pressure in the water. The water itself only goes as high as that upper confining layer. But in the case of the unconfined aquifer, it's the water surface that's drawing down. And the equation looks very similar, but there's a subtle difference. Now we're squaring the elevation term, H2 and H1, and then rather in terms of being, instead of being in terms of the transmissivity, T, now it's just the hydraulic conductivity, K. So slight difference. We'll work an example here where we're trying to find the hydraulic conductivity based on the water surface that's described. We know that there is a monitoring well some distance away from the production well, and that's how we know where the water surface is. You don't know it just by looking at the dirt, or you can't pound a nail in and know what the depth is. The way that they actually would know what the water surface looks like is you have to drill another well until you actually get to the free surface of the water. So in this case, we've got the main production well here at the center line of the problem. Since these are radial problems, we consider the production line at the center of the universe, so to speak. And 50 meters away from the well, so location 1, R1 equals 50, we are given a certain drawdown. Now, these equations are written in terms of the height of the water above the bottom confining layer at that location. And so drawdown is talking about where the water used to be before the well started versus where it is now. So this distance from the old water surface to the existing water surface is the drawdown. And in the problem statement it's saying that the drawdown 50 meters away is 1 meter, and then 100 meters away at location 2, the drawdown is ½ a meter. So we can calculate the hydraulic conductivity just by rearranging the well flow equation. Before we do that, let's just get some of the preliminaries out of the way. 0.4 cubic meters per second is the flow rate. The original height of the water table is 24 meters. R1 is 50 meters. S1, S being the variable for drawdown, is 1 meter. So H1 is 24 meters minus 1 meter equals 23 meters. R2 is 100 meters. S2 is 0.5. So H2 is 23.5 meters. And it's the K value that we're interested in here. So we have the original well flow equation. We can rearrange that in terms of K. It would be QW times the natural log of R2 divided by R1 divided by pi H2 squared minus H1 squared. Okay, so that is 0.4 cubic meters per second. ln of 100 meters divided by 50 meters divided by pi 23.5 meters squared minus 23 meters squared. So when we put all that in the calculator, it turns out that the K value is 3.8 times 10 to the minus 3 meters per second. In the equation manual that they provide you for the FE exam, they have both the unconfined and the confined aquifer equations available, and so it's really important to pick out the right one. Guaranteed that one of the distractors on each problem that has a well flow equation application, one of the distractors is going to be picking the wrong equation, and they look really similar, so it's easy to pick the wrong one. So you have to look at the problem statement to see if it says it's confined or unconfined, look at the drawing, and know the difference between what they look like. I guess on the final exam it could be the same way. I'm not going to provide you with the equation. You should include both on your equation sheet, the confined equation and the unconfined, and know which one to use. Any questions about this example? Yeah. Sure, yeah. The way that you know this is unconfined is, first of all, that they've got the triangle on these little dash marks here. That tells you that this is actually water that's drawing down and not just the theoretical piezometric surface. So that's one clue. But I guess the biggest clue is that there's not a big thick layer of clay running through the middle of our aquifer. If you compare it to the other example that we worked last time, both of those clues are missing here. You don't have the triangle along the phreatic surface. You know, this is just a hypothetical line of where the water level would rise to if there's a monitoring well. The water is actually confined down here, but the big clue are these little hatch marks here that's showing that's a confining layer. Other questions? All right, so these are really simple problems, these well problems, and we're making them even more simpler by assuming that all of the soil has the same hydraulic conductivity. Of course, that's not true. You've looked at soil maps before. You know the Sergo soil maps that you downloaded for WMS. You know it just looks like it's total pandemonium and lots of random different shapes all over the place. And so if you've ever dug a hole, you know that's true. You may have a patch of sand here, a bit of clay there, gravel. It's just underground is very random, and it's not always going to be the same material unless you're like in the middle of the desert or something. So oftentimes there's more than one material that water is flowing through. And what's pictured here in this sketch is that there are two different either reservoirs or two different lakes, two different, two rivers. Anyway, there's two different pools of water, and the elevation of the water on the left is higher, And so that's going to be forcing water through the soil that separates pond left and pond right. There's these two different ponds. Water is going to be migrating towards the pond on the right because it's a porous medium between them. It's not concrete, it's not plastic lined, it's soil. But there's two different soils there, K1 and K2. Soil 1 has a different hydraulic conductivity than soil 2, and you can see that the thicknesses are listed there. So this is kind of a complicated problem, and it's not radial either. It goes some distance into the page. You can see, well, I don't think I've defined that variable, but we will in the example that we're going to work. It goes into the page some distance, and so what we're going to calculate is the flow through this porous medium on a per meter basis. And by per meter, what we mean is one meter into the screen. We assume that there's two rivers running parallel to each other, and we want to know how much water is going to move from the river on the left to the river on the right through the soil for every meter that they are running parallel to each other. And you can see the development of the equation here. The derivation of it goes into some detail in the text. I'm more interested in having us get a chance of the application. You can see that the flow rate between the two depends on, for one thing, the slope of that surface. And so, as you might guess, the difference in the elevation between the left river and the right river is going to drive flow between the two different ponds. If they have the exact same height, there isn't going to be any driving force that moves the water from one place to the other. If they're the same height, then the water surface inside the porous medium would be the same, and so there's nothing that would cause the migration of the fluid. So let me just show you what these calculations look like so that you can have some exposure, and I'll calm your fears by letting you know you won't have a problem like this on the final exam. I'm going to just go right ahead and say it, but I still would like to acquaint you with what this looks like, because if you do take like a full-fledged subsurface hydrology class someday, maybe at the graduate level, this sort of problem is going to be your bread and butter. You'll do lots of these. Okay, the canals are a kilometer apart in this example. And you can see that we've got two different formations, a limestone formation with one K value that's relatively low, and then a Fort Thompson formation, whatever that is. I don't know if it's a clay, or I guess it's going to have, it's a pretty high hydraulic conductivity, so I guess it's not clay. So this is subsurface flow between reservoirs, and the height of the water on the left, we're given the elevation of the water surface and the elevation of the base of the aquifer. So let's just find, first of all, HL and HR. The total height of the water is the 1.07 elevation that is being specified minus 15.24 meters. So that's 16.31 meters. And the height of the water on the right is 1 meter minus 15.24. So that's 16.24. If you think about, that's, yeah, okay. There's not much of a driving force there. They're a kilometer apart. That's pretty far apart. And the elevation difference between the two of them is 0.07 meters. So it's a very slight elevation difference in the water surface. Let's get the thickness of B2. It's negative 3 meters minus the 15.24 meters. So 12.24 meters. The K1 was already given as 1,500 meters per day. K2 is 12,000 meters per day. And the length is that they're 1,000 meters apart. So we have to find these coefficients before we can actually find the flow rate. We have to define C1 and C2 so that we can use this equation that's boxed. C1 is K1 divided by 2L, the height on the right squared minus the height on the left squared, plus K2 minus K1, B2 divided by L, HR minus HL. Okay, so that is 1,500 meters per day divided by 2 times 1,000 meters, 16.24 meters squared minus 16.31 meters squared, plus the sum of the two hydraulic conductivities, not sum, difference, 1,500 meters per day times B2 divided by 1,000 and 16.24 minus 16.31. So when we do all those calculations, we get that the C1 coefficient is negative 10.705. We go through a similar process of finding C2, and after all the substitutions, get C2 is 2,295,673. Okay, so the equation that we're going to substitute it into is K1 divided by 2 H2 plus K2 minus K1 B2 times H equals C1 times X plus C2. So that is 1,500 divided by 2 times H2 plus 12,000 minus 1,500 times 12.24 times H is equal to negative 10.705 plus times X plus 2,295,673. With this, you can solve the equation both in terms of H and X. We rearrange it, it looks like this. H squared plus 171.4 H is equal to negative 0.01428 X plus 3061. So asking for the phreatic surface as a function of x, what that means is that as you move from left towards the right of the canal, so you're going to be able to know what is h, you can solve for h as a function of x. You put in how far you are, x is in meters, and that's going to describe the curved surface. The curved surface between the two is looking like this. You know, it's gradually getting lower and lower, and it's a non-linear surface. It has a curve to it, and this equation is going to describe that curve. As for the flow rate, it's actually relatively simple in this case to solve for the flow rate. The Q is just the negative C1, so it is 10.7 meters squared per day. And I want to really emphasize the units of that. Meter squared per day, when you have two rivers that are running parallel to each other like we have here. So here's the soil, and then here's river 1, river 2. Basically, what we're trying to find out is how quickly is water moving between the two rivers, like it's seeping through the soil this way. And so the rivers both have depth, which is shown in this cross-sectional view, the height of the water here, and they also have length. And so this flux, the 10.7 meters squared per day, means that for every meter of length that they run parallel to each other, you'd have 10.7 cubic meters per day of flow between them. So it may be that they are just close to each other temporarily. Like here's the two different rivers. So here's River 1, here's River 2, and then they both get further apart. And obviously the further apart they are, the less is going to migrate between them. But if you know this length that they are in close proximity, then you'd multiply that length by this, and then that would tell you how much flow is actually being lost from River 1 towards River 2. All right. So that is the end of the semester. I'm going to open up the tablet cart, and what I'd like you to do is, if you haven't already filled out the evaluations, log into MyMU. You've probably been getting the reminder emails for it. Do they send those to you every couple of days? I don't care if you do your evaluations for your other classes. Just do your evaluations for this class. This class is the one that, I like your feedback. I'd be glad to know if you have any suggestions for how the course could be improved from the learning perspective. So